Hi, I'm Bob. Welcome back to 5 Minute Econometrics, a program for econometric learners. In previous videos, we have learned the t-test for a single parameter in the model. It usually tests the statistical significance of individual explanatory variables. Then we learned the hypothesis tests for a single linear combination of parameters in the model. After placing the linear combination on the left-hand side, we can define a new parameter and transform the model so that it becomes a t-test for a single parameter. Testing one parameter or one linear combination of parameters involves a single linear restriction. Today, we will deal with something new, the hypothesis about multiple linear restrictions. The first case is whether a group of explanatory variables has no effect on the outcome variable. For example, this model relates baseball players' salaries to their years in major leagues, the average games played per year, and three productivity performance measures: career batting average, home runs per year, and runs batted in per year. Suppose we want to test the null hypothesis that once years in the league and games per year have been controlled for, the three performance variables do not affect salaries. Essentially, the null hypothesis states that productivity as measured by baseball statistics has no effect on salary. The null hypothesis is that beta 3, beta 4, and beta 5 equal 0. The null hypothesis contains three exclusion restrictions. They are called exclusion restrictions because if the null hypothesis is true, then the three performance variables should be excluded from the model. It involves more than one restriction on the parameters. There were three exclusion restrictions now. The hypothesis test for multiple exclusion restrictions is called the joint hypothesis test, or the multiple hypothesis test. The alternative hypothesis is stated as the null hypothesis is not true. The joint hypothesis test for multiple exclusion restrictions is called the F-test. The F-test concerns two models: the restricted model and the unrestricted model. The restricted model is the model in which the restriction is imposed. The unrestricted model is the model without the restriction. The restriction is that the three coefficients of the performance variables are 0 in our case. So, the restricted model must be shorter than the unrestricted model. The F-test compares the sum of squared residuals from the restricted model to that from the unrestricted model and determines whether the change is large enough to reject the null hypothesis. The sum of squared residuals is a measure of the variation of the outcome variable that cannot be explained by the explanatory variables in the model. Since the restricted model has fewer explanatory variables than the unrestricted model, the sum of squared residuals in the restricted model must be greater than the sum of squared residuals in the unrestricted model. In our example, the sum of squared residuals from the restricted model is 198. and that from the unrestricted model is 183. The variation of players' salaries that can be explained by the model decreases when the three performance variables are excluded from the model. In other words, the unexplained part of the variation increases as those three variables are excluded from the model. Whether these three variables are statistically significant depends on the relative change. That is, the change in the sum of square residuals relative to that from the unrestricted model. The F statistic is defined as follows. The numerator is the change in the sum of squared residuals, and the denominator is the sum of squared residuals from the unrestricted model. Both are adjusted by their degrees of freedom. The numerator degrees of freedom Q equals the number of restrictions, and the denominator degrees of freedom n minus k minus 1 is the unrestricted model's degrees of freedom. If the relative increase in the sum of squared residuals is large enough for a chosen significance level, then we reject the null hypothesis that three variables are jointly insignificant. Under the null hypothesis, the F statistic has an F distribution. We can read the critical values in statistical tables. The rejection rule is that if the F statistic is greater than the critical value, then we reject the null hypothesis in favor of the alternative hypothesis at the chosen significance level. In our case, the F statistic can be calculated as follows. The sum of squared residuals from the restricted model is 198. The sum of squared residuals from the unrestricted model is 183. The numerator degrees of freedom are 3. The denominator degrees of freedom are 347. The F statistic equals 9.55. From the statistical table, we can find the critical values for 10%, 5%, and 1% significance levels. The 1% critical value for numerator degrees of freedom of 3 and denominator degrees of freedom of 347 is 3.78. The F statistic is above it, so we reject the null hypothesis that the performance variables have no effect on the players' salaries at the 1% significance level. The three performance variables are jointly statistically significant at any conventional level. Keep in mind that the individual t statistics may give misleading information on the joint statistical significance. The t statistic for each performance variable indicates they are individually insignificant even at the 10% level. It seems that they should be jointly insignificant. However, that is not the case. The reason relies on the fact that two of the performance variables are highly correlated. The strong multicollinearity leads to individual insignificance, but it is much less relevant for the joint significance. Today, we have discussed the F-test for multiple exclusion restrictions. Thank you so much for watching this video. See you soon. Take care. Thank you for watching this video and subscribing to my YouTube channel. See you next time.